about not its status, but reminding people kind of its background and where this idea came from. So I'd like to convince everyone that prompt optical emission, the rise phase of the optical light curve, I'm not talking about the afterglow, not talking about a little bit of trailing off at the end, I'm talking about the rise phase, has a lot of interesting physics in it and touches on interesting topics. And this is what you could do if you could respond fast enough to catch this initial optical rise. We think that you can, using simple assumptions, you can, from Molinari et al., 2007, you can get kind of an estimate of the bulk Lorentz factor just by looking at the time of rise. And as you can see in here, you just, okay, look at the rise time and you get a bulk Lorentz factor. And of course, looking in this thing, you end up with the kind of Fermi-like factors of 1,000 at 10 seconds, and you can get, faster or slower. For a BLF of about 1,000, like the Fermi kinds of values, you need to respond faster than 10 seconds. Again, that's why we have this very fast response system. You can identify if the origin of the prompt optical emission is internal shock or not by looking at, does it look like a gamma ray burst? Is it this very quick thing? Or does it look like this smooth, nice thing that comes up like that? Some of them we've seen look like either one so far. And you must have to be much faster response with much faster time resolution than we have now to do this. I want to remind you that if you had a big sample of optical and gamma rays in prompt, you could do all kinds of interesting things with it, all kinds of interesting correlations. And as far as whether they correlate or not, there are both examples and counterexamples. And there's this very nice example of 04-12-19. Here is 99-01-23. No way. No, couldn't correlate. And some kind of intermediate case for the naked eye burst. I think I briefly mentioned this in the previous talk. You can think of doing messenger measurements, what they call this. Look at the correlation decay okay, now you have the gamma ray bursts, and now you gamma and X and optical. Okay, and then you might even have gravitational waves and neutrinos for the same event. That would be really cool. You can look at GR alternative models by looking at this enormous spread in energy from an EV to MEV. And have a great lever arm there in energy. And these timescales can be potentially very short, and you need faster response than we have already. I think you've seen this. I'm going to skip over this. So we've been hoping there's going to be a GRB luminosity calibration for years, and nothing has really come of this. There was an interesting paper, Panatescu and Vstrand, 2008, which is a paper I love to refer to because it sort of gathered all the fastest light curves, and it has dozens and dozens and dozens of them. And you realize most of them do not catch the rise. But one of the interesting things they did was they plotted a luminosity and rise time correlation, and you look at this and you go, wow, this is great. We should follow up on that. We should, bet our scientific reputations on that. Well, before you bet your scientific reputation on that, be careful, because in the same paper, they have these many, many light curves which just don't have the rise time. So they plotted, 4 or 5 on that, but the sample is 60. There's something fishy going on. So I wouldn't bet my reputation on this, but I would say it's interesting enough that I'd love to have the data to look at that correlation and see if there's anything really there. Right. So most of the rises are unknown. You just need more data at earlier times. And the UFO project is all about just getting there faster with the optical. So again, Swift has this really this cliff at 60 seconds, and more like it's more typical as 100 seconds. You're missing a lot of these phenomenon. How will we ever get a great sample of these rise times if we don't make an instrument for it? And that's what UFO is supposed to do. I don't want to minimize ground-based telescopes. First of all, we had a very nice talk today about some prompt detections from MASTER, and I wanted to show you some of the interesting ones from ROTC that I have, which shows, okay, a smooth optical here, but notice that they failed to catch the rise. Even if with response as fast as 10 seconds, they failed to catch the rise. Again, failing to catch the rise. And wouldn't you love to know the true distribution of these rise times? Okay. After 7 years of Swift, there are a few detections from ground base of this prompt optical. We have one of these really fantastic cases, but it's 1 in 7 years. That's not an existence proof. It's kind of a proof that you got to do something else. You're never going to get there. You're never going to get enough data to really move forward on this. Swift is not going to be there forever. We need a faster system for a game-changing kind of progress on this. So how do you respond faster? Okay, so here's the Swift satellite. It's pointing over here, but it has an extremely wide field camera. The camera burst is over there, and it says, okay, I'll go. And I'll go tick, 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 tick. And it has to move this entire massive satellite, tick, 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 over until it can finally point at the gamma ray burst. So what is the sense, however, in moving this whole giant spacecraft? Why not just move the mirror?
What's the speed? How many degrees can you move?
Swift? Okay. I think the right answer to that is, I don't care what the engineers say, it's the histogram I just showed you of response times. It has a peak around 100 seconds, and then it falls off completely to 0 by 60 seconds.
The speed of
The speed of Swift, yeah.
100 seconds, what? I mean, how many degrees can you move per hour?
Oh, okay, so, I mean, again, I don't really know the answer to that. All I know is from the time that the gamma ray burst triggers to the time that you detect something, typically takes 100 seconds and is almost never faster than 60 seconds. But everything interesting is faster than 60 seconds.
No, I totally agree, but if you compare with HST, for instance.
Yes, compared with HST, it's much faster. And again, I don't mean to minimize the great job of making Swift pretty swift, but it could be faster. So yeah, you have to rotate the whole spacecraft, and if you want to respond faster, instead of steering a whole spacecraft, why not just steer a beam? Why not just stick a mirror in front of the telescope, which is much faster, and which is what we've done. The way I got into this whole business was our partners at IHWA, Women's University in Seoul, which you'll see me write down as things like IHWA or MEMS or RCMST. It's all the same people. It's Ilpark's lab at IHWA, have these micromirrors. And these micromirror arrays are fabricated just like semiconductors devices are fabricated. And they're very small. These are 0.5 millimeter size mirror segments here. And what's different about these from commercial MEMS devices is that they have extremely large throws. Plus and minus 50 degrees is no problem. Okay? They operate in milliseconds, which is very exciting for trying to steer a beam. And you can imagine putting a mosaic of these devices in front of a telescope and steering the beam that way. Turns out that the limiting factor is the uniformity of manufacture. It turns out that that's worse than the diffraction limit for these little tiles. The problem is they don't all point quite exactly in the same place. So when we looked at these in tests, we found that this was spreading out the PSF as much as 2 arc minutes. So as George mentioned last night, we had an idea where we would have a large plane of these on a platform that rotates. We might try to get ultra-fast prompt response by combining a kind of MEMS steering where each little element would move over in a millisecond, and then you turn the power off. They do go optically flat when the power's off, and then move the platform on the seconds time scale. It turned out that just didn't work so well, and on the actual UFO Pathfinder, we won't be using these at all. We'll be using standard mirror technology. I think I just sort of mentioned all of this.
Just one little question. They can flip on about 2 axes.
2 axes, more than plus minus 50 degrees. They're really, really something, and that's what's different from ours compared to commercial ones. Commercial ones typically are made for things like adaptive optics, corrections, and they're more complicated. They have a piston mode as well, but usually their throw is very tiny. And the other kind of MEMS mirrors, of course, are the kinds of projectors, and they're one-dimensional on-off devices. They're not carefully steered. Here's our little schematic of the UFO Pathfinder. It's a tiny, tiny instrument. It's only about, just over 20 kilograms. I'm sure we cheated and got a little bit above that. Only about 10 watts, I'm sure, again, we cheated, got a little above that, but order of magnitude. It's going to be mounted on the Lomonosov instrument platform up here with BDRG Shuck and all of the instruments from our partners here at MSU and SINP. It has a coated mask camera, just like kind of a micro Swift. It has a beam steering mirror and an optical path goes out that sun shield there. There's some electronics, the detector plane, the primary mirror, our ICCD detector, and our beam steering mirror. One of the points that I didn't really make in my last talk was that it has the coded mask and the optical follow-up, kind of like a micro Swift. But one thing that it's very much missing compared to Swift is it doesn't have a pointed X-ray telescope. So Swift can do really, really cool things like just using the X-ray telescope, looking at the afterglow, it can give you arc-second positions. And that's amazing and wonderful. And you can go do stuff with galaxies, even though you never got an optical signal. However, for this kind of small, fast, quick, cheap idea, it's still, I think, worth considering the concept that you just go after the bursts that have a bright counterpart. Okay, when you just go after the bursts with a bright counterpart, kind of like our friend's scheme here, they're bright, and you can take spectra of them, and you can keep looking at the afterglow, and okay. So there's lots you can do with them. So that's one nice selection of it. Here is the only part of the talk that has the actual update that I'm supposed to be giving. Here are some pictures of the actual devices. So you'll see this hopper here is passive multi-layer shielding, and down here is the detector plane for the X-ray detector. So again, some gamma ray burst goes off, the photons come in here. This is a shadow mask. It casts a shadow on the detector plane by looking at, okay, just like any shadow, the light source goes over there and the shadow goes over here, light source goes over there, shadow goes over there. Just like any shadow, you can tell where the source is by deconvolving the actual pattern on the detector. This is the actual, what's called the SMT, or the slewing mirror telescope. This is the actual beam steering mirror here. The hood is up. This would normally be in a position where we folded down over, and the light comes in through the sun shield there. So this is our flight model, and this is a little base plate that's bolted onto the instrument platform. Here you can see we're doing a little test with parallel light in the actual SMT and the steering mirror. And right now, the UFO is at ISTRA, undergoing tests with integration with an interface with other instruments. So this is our beam steering mirror right here. And what is limiting is when you're talking about things in the 1 second slew range, the limit is not really how fast it takes to get there, but rather how fast it takes to settle. So if you look at our data here and the settling times, and you'd see we get down to the arc-second range around 300, 400 milliseconds. So our fastest response will probably be around 400 milliseconds and up to about a second. We have a very nice mask made by our collaborators at the University of Valencia. And again, this just shows a little bit more of a cutaway, the mask up here, the hopper and shielding here, the detector plane here, the electronics underneath. Our mask is tungsten. We have a very unusual detector. Our detector is read out by MAPMTs, and here we have YSO crystals. The reason we ended up with this is we had a very, very short time to do this project. We tried to get good electronics for CZT detectors, and we were unable to do this in the time frame necessary. However, we have connections to the GEM USO collaboration. We were able to have their ASICs to read out all these MAPMTs. And so that's the motivation behind this very non-standard kind of detector. This is our UFO digital board for readout. And this is one of our spectra. Yes?
This is a Spassky rock. It's made in Paris 11.
I think so, yes. I think so, yes. These are numbers that are mainly for me in case anybody asks any questions. But some of the things I want to point out, it's only 200 square centimeters, very tiny. And we have 48 by 48 channels. Here we are in Istra. That's Vasily. That's Nikolai Vedenkin, who is here from.
This evening, and Vasily was here yesterday.
And they're from MSU, and they're in here working on it, testing this. The SMT instruments is now being tested at ISTRO. This is some multi-layer insulation, and that's Nikolai again working with one of our people from Korea, from the RCMST. This is an electronics box for SMT. Here's our mirror. You can see that. Okay. And some of the details of spaceflight, we're doing things like stuffing epoxy on all these boxes, getting them ready for spaceflight. Here we are working at the ISTRA facility. Here's our expert team, which includes Go-eun, Soo-min, Era, and Ji-yoon. Here checking the power boards. We spent a lot of time at the facility, assembly facility in ISTRA, retesting, assembling, and so forth. I hope that some of our tests are a little bit more sophisticated than this, but here's how we check the repeatability of our pointing for the moment, getting it down to 10 arc minutes. The idea of our mirror is not so much to point so precisely. We have a field that's slightly larger than we have a 15 arc minute field for our camera. We don't want to point to a single pixel accuracy. To update our schedule, in about 2 weeks, we'll be doing the flight model bus interface input control test. In early July, we'll actually attach the whole thing to the payload frame of the spacecraft. We'll do integration tests between the BDRG instrument, which we just heard the talk about, and an SMT to try and be able to trigger off of BDRG triggers. This is, again, our field is too small to get a very large yield from BDRG, but what if you have a failure of UVAT? It's still a nice thing to have. And also, it would be nice to have data from BDRG and Shock and SMT all at the same place and time. And then in July, we'll be delivering this thing to VDM. I'm not sure when the final cross-calibration is scheduled. That's a kind of a question mark for me. And our best launch estimate now is 2013 April. We want to, when we're done with UFO, we want to sort of go beyond this and want to have a next generation mission with a lot more area. We want to sort of attack some of the problems that I talked about this morning. And I think I went over most of this. So I'm not going to dwell too long on any of these. Stop me if you have any questions. I just want to remind you that it's like, again, sort of the same mini Swift idea. A coded mass camera. Now we're trying to get up to 1,000 square centimeters, which we think we can fit in 120 kilograms in a next generation mission. Again, we have a steering mirror on a 30 centimeter telescope to try and get up to the same aperture size as Swift. And we want to use this dichroic to have both an optical and an infrared camera on the same, at taking images at the same time. This is based on a kind of typical teledyne sensor with a nice, clever Leostop and Narcissus baffle design, and a pretty standard CCD camera. Again, I'm excited about that desk business there. We're going to be, the tough part is keeping the sensor cool. The IR sensor wants to be very cold to get good results. There's a nice thing by Thales, however you pronounce that, aerospace, which is called an LPT cooler, which we found that can do this job quite well with very reasonably low power. And the RI cam, that is this infrared camera, is going to be really sensitive, even though we all have a fairly small aperture. It has, we chose a short cutoff, a 1.7 micron cutoff to cut off all the thermal background. We have a Leostop and these nice baffles to give us a good design and no internal background, and a big wideband that goes from 6,000 angstroms to almost to 2 microns. This is really the way to win. Okay, wideband, low space background. You have a steep object that's bright in the infrared. This is the way to get it, to get faint bursts. Okay, so I have some very optimistic sensitivity estimates here. If you look, if we can continue our exposure up to 100 seconds, which is not clear depending on the pointing, but we could get way down here. These are equivalent V magnitudes, assuming a constant slope, way down past 20 magnitude in these very rapid exposures. Why do I claim this is so sensitive when Swift did all this work to try and make a sensitive camera and all this? 2 reasons. One is that Swift has a terribly antique detector, which is in the wrong waveband. It's basically a UV blue sensitive detector, and it's very old technology. And second of all, Merck had TEL devices, they just kick you know what. This is the efficiency of the MCP, the microchannel plate on Swift. Look at the efficiency curve of Merck had TEL, okay? Above 80% all the way from 5,000 to 2 microns. We actually do have a plan on UFO, and I'm not sure whether this is completely implemented yet or not, to transmit immediate alerts via Globalstar. We don't have TDRS access, but we have this Globalstar system, which basically means that we take a chip that has a cell phone in it, and we stick it in the camera. This is Nikolai Vandenkin did this for us, and we're going to actually be able to get out alerts. And so I hope that all of you who have access to optical will be able to follow up on these. We do already have our colleague Alberto Castrotirado with his Booties network. It's going to be following up. We will be on the GC end, and we hope you'll follow up with us. We're giving optimistic estimates like we're going to be detecting 15 in the optical blue channel and about 29 in the infrared channel. We get a number like this that's so impressive, even with a relatively small number of CGRBs, because we'll get every one, no matter how extinguished. We'll get almost all of them, even the fairly extinguished ones, because we're going all the way out to 1.7 microns. We'll be on it very fast, and I insist on putting a greater than symbol here, because a lot of these bursts we expect to be brighter very early from prompt optical.
And also the high redshift.
I'm sorry?
Also the high redshift of the infrared camera.
I'm not counting on that one. These numbers come from not assuming that it'll be brighter earlier. These numbers come from the same statistics as Swift, just saying how many do they actually get an optical candidate from in each brightness bin. That's where I got those numbers from. But I think it's going to be a larger. It has potential to be a larger number. Is the right way to say this. So here's what I'm going to do something absolutely awful and terrible that I should never do. I'm just making up data to show something potentially cool. This is the current detection time histogram. These are detections in blue here. Wouldn't it be cool if instead of starting in 100 seconds, the detection histogram had bumps at 10 seconds, 1 second, and even fractions of seconds? That's what we're looking for. So the last thing I have to say, I think I've just gone over this to death. I'm not even going to go through the summary again, although I just wanted to mention we have possibilities of getting a sample, a large statistical sample of rise phase light curves, some sub-second measurements, bulk Lorentz factors, rise times, X-ray optical correlations, possible multi-messenger measurements from this kind of fast response system, I think I just want to mention that all our projects are open to follow up and other kinds of collaborations. I really want to close by mentioning that this is not my work at all, except in part. The actual UFO project, PI, is ILPARC. And we have lots of people working very hard at the RCMST in Seoul. We have been having lots of cooperation and help from people here at MSU and SINP, including Sergey, who's here, and Professor Panasuk, I think he's gone. I also want to mention lots of help from George and the IEU. And I'm just going to close with our movie of Exercising Our Mirror. And I'll take any questions.